Hello Dynamics, welcome back. Let's do an example with kinetic energy, or work equals change in kinetic energy, and let's do this for a set of several solid objects. Okay, so here I've got two rollers, and we'll assume that they are attached on some fixed axis, but they're free to roll without any friction, and I've got some weight here which is driving the rollers, causing this 30 kilogram mass to move to the right. So what I want to know is, after this mass has moved 2 meters, how fast is it going? And maybe we could figure out how much time it took to travel that distance. So maybe you care about this because you're designing some device that's supposed to move packages along a belt, just in case hypothetically there was some kind of surge at your FedEx or UPS sorting center, lots of packages, just hypothetically. Okay, so we learned in the previous video that we can describe the kinetic energy of a particle as its translational kinetic energy plus its rotational kinetic energy. In fact, we had this formula. We had kinetic energy was 1/2 the total mass times the velocity of its center of mass squared plus 1/2, that was the translational piece, plus the rotational piece was 1/2 I omega squared. This is the kinetic energy of a particular solid object. So for this problem, I'd like to find the work done on the system, set that equal to the change in kinetic energy of the system, and use that to find the velocity of this 30 kilogram block. Okay, first, what's the work done on the system? Well, the work done on the system is the force of gravity pulling this 10 kilogram mass down. There are lots of other internal forces in the system, but we're looking at the net work done on the system, which is just this force of gravity pushing or pulling this 10 kilogram mass down. Now, does this force of gravity do negative work or positive work? Well, in this case, the force of gravity is down. The motion of the 10 kilogram block is down. So if you calculate the work using the integral of f dx, then you're going to get a negative times a negative, which makes a positive. Or another way to think about it is, if that work would tend to speed something up, that means it's going to be positive work done on the system. So we have positive work done on the system. The amount is the force of gravity, 98, times the distance. Now, the distance, this 4/3, wasn't given. What is given is that the 30 kilogram block is going to move 2 meters to the right. So we have to do a little bit of figuring out to see how far down is the 10 kilogram mass going to move if this 30 kilogram mass moves 2 meters to the right. Okay, so to do that, we'll figure out what angle this left wheel has to rotate. So for this mass to move 2 meters, the distance traveled by the edge of the wheel has to be 2 meters. So the arc length that rolls off that left wheel has to be 2 meters. And we know arc length is radius times change in angle. So if the radius is 3 meters, then the angle of rotation has to be 2/3 radians. And of course, the angle of rotation has to be the same for the outer wheel and the inner wheel. So if the theta, down here I've written the expression for the inner wheel, which is where the 10 kilogram mass is attached. So we would take that angle of rotation, multiply it by the inner radius, which is 2, and we get the distance traveled by the 10 kilogram mass would be 4/3 meters downwards. So the total work done then would be 98 times 4/3. Now, how about the change in kinetic energy? Well, you got the kinetic energy of the 10 kilogram mass. That has a translational piece, but not a rotational piece. The 10 kilogram mass is not rotating. Then you've got the left disk. That is rotating, but not, there's no motion of the center of mass of this left disk. So it's rotating but not translating. Same thing with the right disk. Rotating but not translating. And finally, the 30 kilogram mass has a kinetic energy due to translating because it's moving, but no rotation. The 30 kilogram mass is not rotating. Okay, so those are our kinetic energy pieces. We're almost done, except we have what looks like too many unknowns. We've got V10, omega 1, omega 2, and the velocity of the 30 kilogram mass. Luckily, we can easily relate these to each other. I think just looking at the picture, you can tell that omega 1 and omega 2 have to be the same. But let's go ahead and relate the other masses, or the other velocities, to each other. We'll do that by looking at this picture over here. Indicate a point A and a point C. Point A is on the edge of the inner disk. Point B is on the edge of the outer edge of this disk. Okay, let's just clean up some details on relating these velocities together. Velocity of point A is equal to velocity of point C plus the velocity of A compared to C. We can write that velocity of A compared to C in radial and transverse coordinates, which gives us 2 omega theta hat. Notice that though for point A, the theta hat direction is in the positive j hat, so that theta hat becomes plus j hat. So the velocity of point A is 2 omega in the plus j hat direction. Now if you look at point B of course can also be written as 2 omega in the theta hat direction, but the actual velocity of the box is going to the right, but at point B the theta hat direction is to the left. So if I write the velocity of the box in the theta hat direction, I have to have a minus sign there. The box is moving to the right, but the theta hat direction is to the left. So the velocity of point B is actually negative 2 theta hat. And then if I set the negative 2 equal to the 3 omega, I get omega is negative VB over 3, and plugging that into my equation for VA gives me this expression for VA. Okay, now you would have gotten away with things here if you messed up a minus sign, because a lot of these velocities are squared, so squaring a minus sign makes that error go away. But nonetheless, it's aside from a handwriting problem on my end, I think plug those relationships into our kinetic energy formula up here, and we get this relationship, which you can solve for V to be 2